so this is chapter 16, completely integrable Hamiltonian systems. And I think the idea of it is that we essentially have, so we have a system of equations with n degrees of freedom. And similarly with it, they just call it n conservation laws. They put in quotes. So n.
So that's the definition of completely integrable. So if you have n conservation law, if you have less, then it's not completely.
Yeah, and then they go through that and they actually show some of the details. But essentially, so we have this and conservation laws, which are and linear. Let's see, they are equations with linearly independent gradients, I believe.
Let me make one remark. Well, there is another definition. Of course, if you have n, then it's fine. But if you have infinity, then, well, infinite many degrees of freedom and infinite many conservation laws, and they're not necessarily equal. So it's like you have, say, if you have a three-dimensional space, then every vector, then your basis has n elements, and so you say that this is a basis if every vector can be expanded anytime. So you say that the basis is complete. You have to take three vectors. It's complete if every other vector, basically if it's linearly independent.
Yeah.
And the same thing here. Well, if another kind of definition in infinite dimensions, at least, this would be that it's completely integrable if every integral can be expressed in those that you have.
Okay.
So, but that's for finite and many dimensions. That's it.
All right, so for they basically consider that we have or I guess a specific case is we have some open set within R2n, which has the symplectic form. Let's see if I can write this right. N is 1 to n d. No, it's regular d. Okay. Yeah, so it has that symplectic form, or similarly, we could just define the same thing on a 2n dimension symplectic manifold. All right. Yes, and we then have n equations, which are conservation laws essentially, uj, such that the Poisson brackets of uj.
So what is uj? These are not equations. These are some
They are
quantities, some functions.
Yeah. So that uj uk is equal to 0, which I just think is another way of rephrasing
Right.
the linear independence of the gradients.
Right. What do you call gradients?
They what they say it was.
These uj are not gradients, right?
No, I think it's they equal something which is equal to the gradient of like the associated energy field. Is that right?
Well, maybe, yeah, but so far this is not what. Okay, when we come to that.
Okay. Yeah, they mentioned that they mention they mentioned that the function u1 equals f could be the energy function whose Hamiltonian vector field we want to analyze.
Oh, okay. So of course, Hamiltonian. We have a Hamiltonian system. The very first, which always exists, is the conservation of energy, which is the Hamiltonian itself. So the first one function of this is the Hamiltonian. Okay, and so that's why that's what you just said.
And then the remaining one they call the auxiliary functions,
Okay.
which are reflect the other conservation laws.
And there must be some way of saying that they are independent in some way. Of course, if you take U2 equal to a constant time U1, then of course we will have that, but it's not an independent one. It has to be functionally independent.
Let me say. Okay.
Is that pretty much?
All right, so they then say that what we want to do is, from this, represent the, they want to represent the flow on the Hamiltonian as a quadrature of, I think, of the elements of the set
Okay, let's just stop.
And then, yeah.
We have h, and then this is what uj.
Yes.
So you take one of these functions and you, well, you treat it as a Hamiltonian, you write it vector Hamiltonian vector field, and you write Hamiltonian equations, and then there is a flow for each one of these, right?
Yes.
Okay.
And they want to represent that as a quadrature of those functions, and they find the quadrature as, let's see. It is a composition. Yeah, it is.
You say of the following functions?
Yes, a map is defined as a quadrature if it is a composition of the following, or I guess operations is probably, yeah, operations. not
Yeah,
functions.
because algebra is not a
Yeah,
function.
absolutely. Operations, which are elementary algebra, differentiation, integration, or the inverse of maps.
And what kind of map is this? I mean, it's a map on that set that you have to real numbers, or what is it? Map from what to what? I guess that's what it is, because that's,
Yeah, I think it's. Yeah, I think it's mapping that
R
set
to
to.
N, or, yeah, was it or theta? This is or?
That, yeah, big.
Or,
No,
okay.
that was
So
the notation they used. Some
map-
open set in R2N.
Okay, map from or to R to N, or?
I think to.
Well, because you have 2n equations, you need to
Mhm.
find all of them, so this will be 2n functions, which means that
Mhm.
map from or to R to N.
Okay.
So you have 2n differential equations, you want to solve them, the result of that solution is 2n functions.
Mhm. Okay. All right. Let's see. All right. So yeah. So after that, and then what they do for most of the chapter now is go through the steps of showing that it's integrable and making or
Do you have to define integrability? Integral means what?
that we can represent it as an integral equation.
Is it integral? Okay, go ahead.
I'm not. I don't think they actually formally define it in here. I think it might be essentially that we can represent the flow as the quadrature of functions, which I think in most of the in some of the examples they give typically comes down to representing as an integral.
Okay, so, what is it, one line about flow, quadrature, that's not a sentence, what is the verb, or what is the statement?
To show, okay, sorry. They want to show that the flows of,
Each one of them.
yeah, each one of them is a quadrature of.
Oh, quadrature, okay.
Yes, sorry.
So basically, this is what you do. You look at n Hamiltonian systems, one for each uj. Okay, so these are different flows. And then each of these will take the first one, the second, and so on. It can be expressed in terms of like multiplication, differentiation, and integration, so integrals of these functions, because these are integrals of motion. Think of it this way, it's like energy, and it could be, there is some kind of symmetry, like it could be orbital momentum, or it could be something else. I mean, each integral of motion represents certain symmetry. There is a theory called Lie theory that tells you that for each symmetry there is a particular conservation law. Okay.
Correct.
I was wondering,
Yeah.
what each of these four operations indicate? I mean,
What do you mean indicate? Well, you take n functions, uj. You could multiply them, you could do whatever algebra, right? You could differentiate them, and you could integrate them and take the inverse map and so on. any operation like this is called a quadrature. In other words, the solution of any of this equation will be expressed in all these functions.
Oh, this is a definition, right?
Yeah, that's
I was
a
wondering
definition.
why
Yeah, that's-
only these four operations, okay. now-
Yeah, that's the
that
definition
makes-
of quadrature.
Well, because usually, I mean, well, take a differential equation, just take, I don't know, second order differential equation. If you take first order differential equation, if you express it, if you find the first derivative, then you can write the solution as an integral. But if you take just simplest second order equation, like linear, second derivative is equal to some function and then some this function, you cannot write it as an integral. Of constant coefficients you can and others. If you can write it as an integral, it's called solution in quadratures, because then you basically solve it. The rest is you just need to compute the integral.